Hi, my name is Martin Rapp. I'm going to present to you one of our latest works with the title Power and Cache-Aware Task Mapping with Dynamic Power Budgeting for Many Cores, published in Transactions on Computers. In this work, we propose a technique to increase the performance of a many-core processor that is operating under a thermal constraint. Our technique comprises two parts, a task mapping algorithm and a power budgeting algorithm. Let me start with the task mapping. The architecture that we target is a many-core with SNUCA caches. Precisely, we use an 8x8 many-core where 64 tiles are connected with a network on chip. Each of these tiles consists of a CPU with its private level 1 caches, a NOC router, and a single bank of the last level cache. The last level cache is logically shared between all cores. In other words, there is only a single logical last level cache. However, this cache is split into 64 banks, where each bank is co-located with one core. The latency of a single LLC access depends on the hop count on the NOC between the tile that executes the thread and the tile that hosts the LLC bank that holds the data. A real application does not access a single memory address, it accesses many. In SNUCA, this results in the thread accessing all LLC banks on all tiles. The average LLC latency that a thread experiences depends on the position of the core in the many-core. LLC accesses from a thread mapped to a corner core on average need to travel farther on the NOC than LLC accesses from the center. So, in order to minimize the average LLC latency, threads should be mapped to the center. However, if we map all threads to the center, a thermal hotspot emerges even at relatively low power consumption. The critical temperature of 80 degrees Celsius is already reached at 1 watt power consumption of the center cores. If cores closer to the corner are used instead, the power consumption can be increased to 1.4 watt while reaching the same maximum temperature. In other words, mapping threads close to the corners results in a higher power budget. This higher power budget may allow operation at a higher frequency and therefore may increase the performance. In summary, from a thermal point of view, threads should be mapped far from each other. However, this results in heavy use of cores with a high average last level cache latency. Consequently, mapping has to make a trade-off between optimizing for last level cache latency and optimizing for power budget. We were the first to observe and exploit this trade-off. The first contribution of this work is a runtime task mapping algorithm that maps unknown applications to cores of the many-core while considering this trade-off. The second part of the proposed technique is runtime power budget reallocation. Some threads may consume very little power, for example because they are highly memory bound. These threads underutilize their assigned power budget. Reallocating their power budget to another thread may increase the performance of that other thread. However, care must be taken to do this in a thermally safe way to avoid violation of the critical temperature. The second contribution of this work is a technique that monitors the power consumption of all threads and performs reallocation of underutilized power budgets in a thermally safe way. Our SNUCA and power budget aware task mapping, together with the dynamic power budget reallocation, increases the performance of the many-core by up to 21% over the state of the art, while still being thermally safe. This is achieved with less than 0.5% runtime overhead. Further details and insights about our technique are described in our paper, which is linked here.